Hi everyone. In this video, I'm going to go through another example where we're playing around with a bunch of function notation. So this time we're going to be evaluating functions represented by formulas. So I have a formula for function f and function g, and we're just going to walk through how to plug in a whole bunch of different things, evaluate a bunch of expressions involving our functions, and we'll do some solve equations and a little bit of composition inverses and graphing, so lots of stuff mixed into this as well. As always, please take this as these are things I'm hoping you've seen, but it doesn't mean it's the end of the world if something looks a little unfamiliar. You just need to communicate with me so that I can give you more materials if needed. So please let me know if there's something that you aren't comfortable with. Okay, so find and simplify each of the following. I have these all cramped on the paper, so I'm going to write on a separate piece of paper as I go here. If I want f of -8, the function f of x follows this rule right here. The rule is that whatever you plug into this function f, it's going to build a fraction, and on the top of the fraction, it will give you the square of your input, and on the bottom of the fraction, it will give you the square of your input minus 2. So my input is -8. If I square that, I get 64. So I'm going to get a 64 over 64 minus 2, which is a 64 over 62. And we can reduce that. I don't even know, maybe a lot. We can definitely cut it in half. Let's see if we can work our way up there. 32 over 31. Oh, actually, I think that's about good. Okay, so I would say my answer here is 32 over 31. A good thing to be really careful with. Ooh, I let autofocus turn back on. Sorry guys, I'm trying to learn my lesson and not let autofocus make these blurry. Okay, so a really good thing to pay attention to in this problem is the fact that this says square the entire input. Some people want to square the 8 and then multiply by -1, so they would have negatives here, and that's not right. If you square the entire -8, you should get positive 64. Okay, next, an f of 2. Okay, so same function, and we've just said that our function takes whatever we give it, and on the top it gives us the square of that thing, and on the bottom it gives us the square minus 2. So this gives us a 4 over 2, which is a 2. And it's completely valid to get what you started with back out of a function. There's nothing wrong with that. Okay, let's see. F of 3 over x. Okay, so same rule. Function f takes whatever we give it, and it squares it, puts that on the top of our fraction, and squares it, puts it first on the bottom of our fraction, then a minus 2. This has some really good algebra review in it. One of the things we run into a lot in calculus is fractions within fractions. So being very efficient at clearing those out is a good thing. So I will show you my favorite way. For starters, let's get rid of the parentheses because those can mix people up. So when we square a 3 over x, we get a 9 over x squared. You should just be thinking 3 over x times 3 over x minus 2. Okay, so one of your choices would be to get a common denominator here. Make this a 2 over 1, multiply by x squared, top and bottom. And then you could combine and have a single fraction on the bottom. The reason that would be beneficial is because when you're dividing a single fraction by a single fraction, you could flip the bottom and multiply. I have a favorite way that's kind of a trick, but I think it's a trick worth remembering since we do a lot of this. My trick is I like to get all of that done at once. I look at this and I say, okay, I have these internal fraction, 9 over x squared. I really wish I didn't have the x squared. I could get rid of that by multiplying by x squared, but you're not allowed to just go and multiply by something. It would change the value of the expression. However, you can always multiply by 1. So this is one of those fantastic algebra tricks. No matter what, it's always legal to multiply by 1. So x squared over x squared should equal 1 as long as x isn't 0, but we already had problems with x being 0, so that's not really a worry. What will happen here is on the top, we get 9 over x squared times x squared. If it helps, you can think about this as an x squared over 1. So the x squareds are going to cancel. 9x squared over x squared is equal to 9. On the bottom, we'll have that happen again, but you need to be really careful on the bottom. There are 2 terms. When you multiply something with more than 1 term, you need to make sure you distribute through. So once again, we get 9 over x squared times x squared, which is just a 9, but we also get a minus 2x squared. So make sure you distribute. That's the one thing in that trick that sometimes gets people in trouble. Okay, so this is a 9 over 9 minus 2x squared. Good thing to point out here is it is not okay to cancel out that 9. Canceling is division, so it's saying 9 over 9 equals 1. And it doesn't make sense to use division to separate the 2 things in the bottom unless they're attached by multiplication. Division will undo multiplication. It will not undo subtraction. So no canceling there. Okay, let me get more paper. F of x plus h minus f of x over h. Okay, so this is messy. This is our difference quotient. It's going to be really important in calculus. Before we get to calculus, we want to be comfortable with recognizing that this thing has something to do with slope. I have a y value minus a y value, and I happen to be dividing by the first x value minus the second x value, so that's a rise over run type calculation. For our function x, oh yeah, this is going to be a real mess. We're supposed to first plug in x plus h, which means it will give us back an x plus h squared over an x plus h squared minus 2. And we're then supposed to subtract off f of x, which is an x squared over an x squared minus 2. And then we're supposed to divide that whole thing by an h. Okay, so this is the f of x plus h. This is the f of x. And then here's our divided by h. So you could multiply out first or not. I think I'll go ahead and do it since I have to rewrite anyways. So I'm going to get an x squared plus 2xh plus h squared. Make sure you're foiling that. That's x plus h times x plus h. And on the bottom, I'll have the same thing with a minus 2, x squared plus 2xh plus h squared minus 2. Again, avoid the temptation to cancel here. Division does not undo subtraction, so you can only cancel if things are attached by multiplication. Okay, so here's where I'm at. This looks terrible, but I'm going to use the same trick, and I actually think, I might be getting overly optimistic, but I think it'll work out fairly well. So we're going to multiply this by, this time because there's different denominators, you have to pick out the LCD, which as terrible as it looks, these two don't share any factors, so it'll just be the entire first one multiplied by the entire second one, entire first denominator. So x squared plus 2xh plus h squared minus 2 times, ran out of room with my big pen, x squared minus 2. And we're going to do the same thing to the bottom. Let's see if I can get it to fit. X squared plus 2xh plus h squared minus 2 times x squared minus 2. So this puts a whole bunch of mess in the denominator, and that's fine. What we're worried about when we're working on these difference quotients is trying to clean up the numerator to the point where you can factor an h out to cancel with this bottom one. That's our big goal. We'd like to be able to plug in 0 for h. That's the calculus part. We can't do that if there's an h sitting, a factor of h sitting on its own in the bottom. Okay, so now the bottom looks like an h times an x squared plus 2xh plus h squared minus 2 multiplied by an x squared minus 2. And then on the top, we have to do the distribute this time. So if we multiply the first fraction by this entire LCD, a nice thing happens. The first factor cancels with the denominator, so it's still fairly messy. We have the x squared plus 2xh plus h squared from the top. We no longer have the bottom. We no longer have this factor, but we do still have an x squared minus 2. And then in the second one, when we multiply, we're left with the minus x squared. The x squared minus 2's cancel, so the rest of what we're left with is the x squared plus 2xh plus h squared minus 2. Man, I made myself a terrible one. I did not make yours quite this terrible, I promise. Okay, so we do need to multiply this out. So let's see, for this first one, I'm going to go ahead and distribute this through to each term. And then for the second one as well, I'll do a distribute, but it's a little easier looking distribute. Okay, so there's my distribute that I'm going to work on. So the first one, I'm going to have an x squared times an x squared minus 2. I'm going to have a 2xh times an x squared minus 2. And I'm going to have an h squared times an x squared minus 2. And then I'm going to distribute a minus x squared, so it's not going to fit. Negative x to the fourth minus 2x cubed h minus x squared h squared minus, plus, two minuses, 2x squared. Okay, pretend that all fit on one line. Over h times x squared plus 2xh plus h squared minus 2 times x squared minus 2. Okay, I'm going to finish my distribute. So I get an x to the fourth minus a 2x squared plus a 2x cubed h, so distributing right here, minus 4xh plus x squared h squared minus 2h squared minus x to the fourth minus 2x cubed h minus x squared h squared plus 2x squared. Okay, now it'll start to shrink. Okay, let's see what goes away. And this is always the goal. And again, I know this one's a terrible mess that I gave myself to do, but yours shouldn't be quite this messy. This is the right idea though. Clear fractions. Once you've cleared fractions, you have this whole mess in the top, but still the big operation is subtraction, so you can't do any canceling of h's. So we multiply it all out, and then we're going to try and combine as much as we can. And our big goal is still to try and factor out an h to cancel with this bottom one. So I see that there's an x to the fourth and a minus x to the fourth. I see that there's a negative 2x squared and a positive 2x squared. I see an x squared h and a negative x squared h. I see a 2x cubed h and a negative 2x cubed h. And I think I'm left with just these two. Okay, so really close. We have made it to, what have we made it to? A negative 4xh minus 2h squared. Okay, I'm going to get a little bit lazy mode here. I'm running out of paper. Over that same thing, we can then factor out an h. You can factor out more than that if you'd like to, but my big goal was to factor out the h. So now I have negative 4x minus 2h. Okay, I'll go ahead and try and fit it in this time. So h times x squared plus 2xh plus h squared minus 2 times x squared minus 2. Okay, and then finally, this was our big goal, right? We get to cancel out an h. H divided by h is 1, and what's left is our answer. So this difference quotient simplified down to, still not very simple, but much better than what we started with. Okay, really big, messy one. Let's see. Use that whole paper. Let's see what else I've got for you. I think that was the worst thing that you'll run into in this example. Okay, we also want to do a difference quotient for g. Ooh, do I want to try and write this one in here? Here, we'll sneak it out to the side. It was x squared plus 2xh plus h squared minus 2 times x squared minus 2 on the bottom. And it was a negative 4x minus 2h on the top. Okay. Next, we want to do difference quotient for g. Okay. So g of x, we haven't actually messed with g very much. Sitting right here, g of x is equal to 1 over the square root of x. So whatever you plug into g, it will give you back 1 over the square root of your input. So the first thing we're supposed to do is give g an x plus k, in which case it will give me back 1 over the square root of my input, x plus k. We are then supposed to subtract off a g of x, which is just 1 over the square root of x, and then we're supposed to divide by an h. Okay, so this one definitely starts off looking a little less messy than the last one. I think it will still get a bit messy, but I don't think it's going to be quite as bad. Okay, so the first thing that jumps out at me here is that I have fractions and fractions like before, so I'm going to multiply top and bottom by the LCD of these two inside fractions, which is the square root of x times the square root of x plus k. When we do this, it once again pushes a bunch of mess to the bottom, but we're okay with that right now. Our goal, K's, there we go. Our goal is to try and simplify the top so that we can factor out a k and cancel. Okay, so here we have to do a distribute. When we multiply the first fraction, the x plus k's cancel, the root x plus k's, and we're left with a root x. When we multiply the second one, the root x's cancel, and we're left with a root x plus k. Okay, so this I think is an improvement. We don't have the fractions and fractions anymore, but I still, there's no way to combine difference between two different radicals. So I still don't have any way to try and combine and separate out a k to cancel. So my next step, this is a good one. It may have been a while since you've been bothered about this one. My next step is to rationalize the numerator. And it's possible that you've never been asked to do that, but hopefully at some point you were asked to rationalize denominators, and it's the same process. The question you want to ask yourself is, what could I multiply the top by to eliminate all square roots? And the answer is the conjugate, which is the exact same thing with a different sign in the middle. The idea here is we're building up a sort of difference of squares thing. So we're going to, this sounds like a terrible plan, but it'll work out fairly nicely. We're going to FOIL out the top. It's 2 terms and 2 terms. And when we do that, it's going to work out really nicely when we multiply the roots by the exact same thing. And then for the inside outside, since we have this difference of squares kind of structure, those two will wipe each other out nicely. On the bottom, we just continue to create more mess and not really worry about it. So we have the k, the root x, and the root x plus k. I would not bother to multiply this out. It's not going to make anything better. We like it all factored. And the bottom is all factored. Everything here is multiplication. The only addition happens within this factor. So the big operation here is definitely multiply. Okay, I'm going to write out all the steps. If you get to the point where you can see what's going to happen and you don't need to write out all the steps, that's fine with me, but I want to make sure everyone sees. So we're doing FOIL. The first is right here, a root x times a root x, which leaves us a root x squared, so just a plain old x. The outside is nothing particularly nice. It's a root x multiplied by a root x plus k. If you'd like, you could squash those together. When you multiply two roots, you can make it a single root and just multiply the x by the x plus k. It's not going to matter in a minute, so I'm just going to leave it. The inside is actually the exact same thing, a root x times a root x plus k, but it has a minus sign, so it's a negative root x plus k. And then the last also has the minus sign. When you multiply a root x plus k by a root x plus k, you get a root x plus k squared. The square and the square root will wipe each other out, and you're just left with an x plus k, but you need to be very, very careful. This will completely mess up your difference quotient if you lose the parentheses. Man, I want to write uphill today. Okay, so let's see. On the top, really nice things start to happen here, so this definitely isn't going to be as big of a mess as last time. I was trying to get rid of all radicals. I got rid of the radicals on the first and the last part, but the middle two, it didn't work out. However, I have a positive root x times root x plus k minus a root x times root x plus k. So even though that's really messy, it definitely goes away. That zeroes out. When you subtract something from itself, you're left with 0. So now what I have is my x, and then I need to distribute, so it's a minus x k over k root x plus k times root x plus k. Okay, which is going to give us a negative k over k root x plus k root x plus k. Okay, and then the magic step, this is the one we were really hoping for. The k's cancel out. So we're left with a negative 1 over root x plus k times root x plus k. And you can multiply some things together or distribute or not. I don't really care. The step that I cared about was that canceling. So that is fantastic. Okay, so let me add this to my answers. Root x plus k k on the bottom and a negative 1 on the top. Okay, so we're getting through some really good messy stuff. Sorry for the beastly long video. Okay, some composition. So those I actually think were by far the messiest, but I do have some more stuff here. So some composition. Let's see. Let's find f of g of x, and I'm also going to mention a little bit of domain stuff because that will come up for us later. So if I want f of g of x, that means we are supposed to take g of x, which is 1 over the square root of x, and plug it into function f. Remember what function f does, I'm pointing up here and you can't see, is it squares your input and puts that on the top of a fraction, and then it squares your input, puts it on the bottom of the fraction, and subtracts 2 on the bottom as well. So this is actually going to work out really nicely. When we square, we're going to get a 1 over x. Okay. And then I'd like to clear the fraction, so I'm going to multiply top and bottom by the x. Don't forget the distribute. This again is the really key step. Okay, so this is what I end up with. and I don't know that I bugged you a lot about domain on your homework. Here, we'll write it right up here. 1 over 1 minus 2x. Okay, but I do want to mention it a little bit. When you do the domain of a composition, you actually have to check two things. One is when we look here, we can see that we don't want to start with x equals 1/2 because that would give us 0 in the denominator. But it's actually even a little more than that because composition is a two-step process. When you plug something into a composition, it first goes to the inner function, and then whatever you get out of that, so the y values of g, get plugged into f. So interestingly, this one right here is telling me that if I start with 1/2, I'm going to get, what is it that f wouldn't like to get? I'm going to get plus or minus the square root of 2. I don't know, whatever it is that won't plug into f. I'm having trouble spotting it off the top of my head right now. So the one that we really need to be worried about here, if I can avoid getting sidetracked, is what would we not even be able to plug into g in the first place? So we need to look back at this g of x formula right here, 1 over x squared, and say, well, to even survive the first step, to have a chance of going to f, we would have to make sure that our x is greater than or equal to 0. So the domain of this thing is, does not equal. X has to be positive, x has to be non-negative, so 0 or greater, and is not allowed to equal 1/2. Okay, we also want to do g of f of x. G of f of x means we should take f of x, which is x squared over x squared minus 2, and we should plug it into g. G is going to give us back 1 over the square root of x squared over x squared minus 2. Okay, so the simplification here, it's actually not as bad as it might look. We want to flip and multiply, but I would say that that could be kind of confusing with the root, so maybe a good idea is to split the root up first. So it's always legal to split roots over multiplication or division. We're going to get a square root of x squared over a square root of x squared minus 2. And then when we flip and multiply, we'll get 1 times the reciprocal. So we get a square root of x squared minus 2 over a square root of x squared. The square root of x squared, I'm very tempted to just make it an x, but we want to think sort of carefully about domain things. The square root of x squared is actually equal to the absolute value of x. So if we want to be really careful, we would say that. I don't know if I want to get into domain here too much because it is maybe a little messy. We can't let x equal plus or minus root 2. And for this one, it has to be bigger or smaller. So yeah, I don't think I want to mess with domain here because I don't really want to sidetrack you guys into something really messy. So we'll just leave it at that. Square root of x squared minus 2 over the absolute value of x. And maybe I would just say, do be careful if you take the square root of x and then square it. That is not the absolute value of x. That'll give you back what you started with, but you have to make sure that you started with something that's greater than or equal to 0. Okay, so those are our compositions. Let's look at our inverses. So let's see if we want to find f inverse. So to find an inverse algebraically, here, let's move back up here so you can see. What you want to do is say, okay, we were looking at y equals x squared over x squared minus 2. You want a function that does exactly the opposite of f. So you want your inputs and your outputs to be switched. So let's let x equal y squared over y squared minus 2. And then we want to solve for y. So I would say first thing that jumps out at me here is I don't want y stuck in the denominator if I'm solving for y. So let's clear fractions. Let's multiply both sides by y squared minus 2. Okay, so I have an xy squared minus 2x, distributing as well in this step, equals, and here they cancel, that was the whole idea there, y squared. And I'd like to solve for y, so let's put them on the same side. I think I'm just going to subtract an xy squared. If you're solving for y, you want your y's all on the same side. So we have a y squared minus xy squared. You could choose to move the y's left and the 2x right as well. It doesn't matter, just pick a side. And then a step here is one a lot of people will forget to do. I can't just combine because this is a 1y squared and this is an xy squared, and I can't combine a 1 with an x. But I still can get down to a single y squared just by factoring out the y squared. So I get a negative 2x divided by 1 minus x equals y squared, which means that y is equal to plus or minus the square root of negative 2x over 1 minus x. Okay, and then to choose the plus or minus, which you should do, in fact, I'm thinking right now that I should have a domain restriction on that problem. I think I gave you one that's not 1-to-1. So let's go ahead and jump ahead temporarily to the graph, and we'll see if we can figure out what I've got going on here. Okay, so this is where we got with a formula. You shouldn't end up with both the plus and minus because that's not a function. So we're going to head over here and say, okay, if we want to sketch a graph of f, that should give us a pretty good idea of what we want for a plus or minus, or if it's even possible to choose. So graphing function f, x squared over x squared minus 2. Okay, so it's a rational function. I don't want to try and use transformations of a basic 1 over x or 1 over x squared because it's too messy. But I can say if the top of the fraction is 0, the whole thing is 0, which means I have an x-intercept, f of x equals 0. So when x equals 0, y also equals 0. And that has a second power on it, which means when we get to that point, whether we're coming from the top or the bottom, we're going to bounce off. The other thing I see here is that the bottom equals 0 if x squared is equal to 2, which means x is plus or minus the square root of 2. So if the bottom of the fraction is 0 and the top is not, we're getting vertical asymptotes, which means at plus or minus root 2, this thing has a vertical asymptote. Oop, get a little far. And then last thing I can get fairly easily from this is the horizontal asymptote. If we're looking for global behavior, which is what a horizontal asymptote is, what happens when you get really far to the left or right side of the graph, you want to think about plugging in really, really big x values. So say we plugged in 1,000,000, we'd have 1,000,000 squared over 1,000,000 squared minus 2. That minus 2 is pretty unimpressive when you're working with numbers as big as 1,000,000 squared. So basically this just becomes negligible, and this is going to behave really close to an x squared over an x squared, which is just going to give you y equals 1. So we have a horizontal asymptote at y equals 1. Okay, if you get stuck at this point and you can't figure out how to get started, it is always fine to plug in some more points to help you out. But I would say one thing I know for sure is that when I leave either side of the graph, I'm going to be really close to the horizontal asymptote. Probably not exactly on it, but really close. So my choices, the first thing I run into is a vertical asymptote. My choices are to start from y equals 1, really close to y equals 1, and either head up to positive infinity at the vertical asymptote or down to negative infinity. And actually I can make that decision without even checking any more points because I don't have any x-intercepts, so I'm not allowed to cross the x-axis to head to negative infinity. Okay, so I head off to positive infinity. If I then think about what's going on here, this one can be a little tricky. It's like having an x plus root 2 times an x minus root 2. So even though the x is squared, it's not the whole thing squared, which means the vertical asymptotes don't have multiplicity 2. They each have a multiplicity of 1. So on this side, if I'm headed up to positive infinity, then on this side, I would head down to negative infinity. The next thing I have to deal with is the intercept at 0, 0. And remember, that one does actually, the whole thing is squared. So that is a multiplicity to deal with, which means we're going to bounce off. And then we either need to head to negative or positive infinity near the asymptote. And once again, we're going to get forced to go the same direction, just continue down, because we don't have any more x-intercepts to get back and cross. Okay, last little chunk here is, let's see, what do we want? This was headed to negative infinity. We had multiplicity 1, so we want to switch back to positive infinity. And then the global behavior is going to take over. Okay, so there's a graph of our function. We don't have to be crazy perfectionists with the rational functions, but we should have some ideas of what they can look like. And we should know how to spot those asymptotes and x-intercepts. So again, if you have any questions, just let me know. It looks like I was bad and I didn't make a domain restriction, and I should have. So this is a perfectly good graph. But if we want to find an inverse for this function, we're in trouble. If we try and sketch an inverse, when we flip over y equals x, we're going to get this sideways u, among other things. It's not going to pass, our inverse isn't going to pass a vertical line test. So basically what we want is for the original function to pass a horizontal line test so that the new function will pass a vertical line test. So I'm just going to impose a domain restriction. I'm going to say, let's require for function f of x, x to be, which way do I want to go? Let's let x be less than or equal to 0. So really we're only going to look at this half of the function. And this half of the function does pass a horizontal line test. No horizontal line crosses the purple part more than once. So this one we could pick out an inverse for. What I would say is if we set our x's have to be less than or equal to 0 for f of x, then that implies that our y's have to be less than or equal to 0 for f inverse of x. And again, don't get too freaked out about this, but the one-to-one thing does come up later, so I wanted to give some people some reminders. Some teachers deal with this more than others. So all the way back to our f inverse, we were trying to choose a plus or a minus. If we want our y's to be less than or equal to 0, that means we better choose the minus. So f inverse is going to equal the negative root of negative 2x over 1 minus x. Okay, so a little bit of trickiness there with the one-to-one. All right, continuing with my monster problem. We're almost there. So let's find a g inverse, which I think, again, is much easier. I keep giving you the hard ones first. Oh, what was this? F inverse is a negative square root negative 2x over 1 minus x. Okay, so g inverse, g of x says that y is equal to 1 over the square root of x. So if we want to find the inverse, we're going to say x is equal to 1 over the square root of y. So first thing, we're solving for y. Let's get y out of the denominator. So I'm going to multiply both sides by a root y. So I have x root y equal to 1. That actually works out fairly nicely. Now I only have one y on the left-hand side, so I just have to get it by itself. Two things are happening. One is the square root is getting taken, and then we're multiplying by x. Since the multiplication is the last thing to happen, that's the first thing I should get rid of. So I'm going to divide both sides by x, and then I want to get rid of the square root by squaring, which means I get y equals 1 over x squared. Here, what was this one? G. So g inverse should equal 1 over x squared. We actually have a little one-to-one thing going on again. This time the problem isn't with the original function that we started with. So here, we'll just graph on our calculator rather than trying to struggle through that. That's not a transformation of anything nice. So if we look at a 1 over the square root of x, zoom standard. It looks, I don't know if you can tell, this is vertical asymptote. It looks fairly similar to 1 over x, but there's only stuff in quadrant 1. There's nothing at all to the left of the y-axis. So we just have this little piece right here. If we put in y equals 1 over x squared, well, here, I think I have maybe an even simpler way to say this. So notice that for the original function, x had to be greater than 0, and y also was always greater than 0, which means down here, we need to make sure we are always going to get outputs greater than 0. So this is for function g, which means that for g inverse, y is greater than 0 and x is greater than 0. X's and y's switch. So we are getting the y greater than 0 because we have the square. But x here in this equation could actually be negative or positive. So we have to force this restriction. So basically, we know, I hope, what 1 over x squared looks like. X squared. Okay, so there's our 1 over x squared. It, once again, is not 1-to-1. It doesn't pass a horizontal line test, so we have to cut it in half. So whether it's the original function that's not 1-to-1 or the inverse that's not 1-to-1, you will always have to figure out how to split it and make it 1-to-1. Okay, let's see. So we got a 1 over x squared, but we have to make sure that x is greater than 0. Okay, truly almost done now. I am hating myself for making such a hugely long problem right now. I get all excited when I can fit everything into one problem until I have to do it. Last couple of parts are just a little bit of solving. So if we want to solve f of x equals 3, that means take the function x squared over x squared minus 2 and set it equal to 3. So when is the output of function f equal to 3? We have rational again, lots of rational because there's fractions in both of our functions. So let's go ahead and multiply both sides by an x squared minus 2. And then I'm going to go ahead and distribute because having x stuck in the parentheses isn't a whole lot better than having it stuck in the fraction. Okay, so let's see. I think I'm going to go ahead and move x's to the left-hand side. So I'm going to subtract 3x squared from x squared, which will leave me with a negative 2x squared. And then I'm going to divide both sides by negative 2. And then I'm going to square root. So I get x equals plus or minus root 3. This was a rational equation, so you do want to take a second to check and make sure that your answer doesn't make your denominator 0, but here it doesn't, so we're in good shape. Okay, so we can say x is equal to plus or minus the square root of 3. And then very last one, pick a different color so you can tell, is we want to solve g of x equals 2 minus the square root of x. So our g of x right here is 1 over root x. So we're going to set that equal to 2 minus root x. And once again, let's start by clearing the fractions. We're going to multiply both sides by a root x. So I get 1 equals 2 root x minus x. So that actually works out sort of nicely. I do have a 2 root x, but root x times root x just leaves me with the x. So I had radicals and fractions. I got rid of the fractions. I still have radicals. To solve a radical equation, you're going to want to isolate that square root and then square both sides to get rid of it. So I'm going to go ahead and add the x. So I have an x plus 1, add the x to both sides, equals 2 root x. And then I'm going to square both sides. Be really careful when you square both sides. You can't just make this x squared plus 1 squared. You have to multiply an x plus 1 by an x plus 1. So you should get an x squared plus 2x plus 1. Actually, careful on this side as well. There's no FOIL, but make sure that the 2 gets squared. So this is 2 root x times 2 root x, which is 4x. And it's quadratic now. So I'm going to go ahead and subtract the 4x, which makes this a negative 2x. So set it equal to 0. And that looks nicely factorable. It factors into an x minus 1 times an x minus 1, which means that x equals 1 seems to be my one and only solution. Once again, make sure you check your answers. So with the variables in the denominator or variables inside of roots, you need to be really careful to check for extraneous solutions. So here, if I plug in 1, I get 1 over 1, which is just 1, equals 2 minus 1, which is also just 1. So I think that's great. Looks like my answer there is x equals 1. Okay, so I think I just managed to cram, at least half of Math 141 Pre-Calc 1 into one problem. Hopefully I didn't just exhaust all of you. Thanks for watching.